It was attached. Okay, any questions on 3 and 4? Okay, let's look at number 5 here. We have B, if B, then not C. Who's got my statement for me? Who's got the statement? In the back corner.
Me?
Yep. If a daisy is a tree, then Android is not an operating system. Hey, a daisy is a tree. Is that true or false? Okay. Android is not an operating system. Which makes this true. Okay, so we've seen every case except for a false true, right? So we've seen a true false, a false false, a true false. Now we need a false true, correct? So we can see what that looks like. In the corner, yes.
Would a false true be true because on a true false it makes it false, and I'm guessing that if a false true would have the true second element true. I'm thinking maybe false.
Let's look at this. If a daisy is a tree, let's do this again. Then Android is an operating system.
No. It's a phone or false. Not an operating system.
So this would be false. And that's true, yes?
So it's false. It's false. Yeah, it's false.
What does the definition say, though? Let's look at our definition. Okay, let's go back up real quick. So if you guys look right here. The conditional statement. If P then Q is the statement that is false if and only if P is true, meaning the first one, and Q is false. So you have to have a true false for it to be false. So if I have a false true, then true. Okay, so it comes back to the definition. So if you know the definition, so we've got several definitions, different statements we've talked about. We've talked about negations. We've talked about just a statement. We've talked about what other kind of statements? Yes?
We talked about conjunctions and disjunctions.
Conjunctions and disjunctions, and then now we have conditional statements, right? Yes?
So, I just think that if that's the only case that it's false, then this is saying, then you'd be saying it's true that if Christmas is on July 4th, because then George Washington was the first U.S. president.
So that would be a true statement. Because George Washington was the first U.S. president.
Yeah, Christmas was not on July 4th. And that's saying that the only way that, basically that's saying the only way that George Washington was the first U.S. president is that if Christmas was on July 4th. So I'm just confused as to how that would be true.
Let me think about it
It's
over
like,
the weekend and get you a better answer. Is that
it's
okay?
like if you're coding a computer, you can say if trigger 939 is activated, run code whatever. But you're saying, but if this were a code, you're saying that that's not true, therefore
you a better answer over the weekend and a better explanation for you. So, this is the best thing I can give you right now. Is the definition. That work? Deal? Thanks. Good questions. Good questions. Okay, so what you guys are going to do is on Monday, your quiz will be anything from questions like 1 through, exercises 1 through 6. That's what your quiz will be based upon. And then kind of a little bit of what we do today was questions 7 and 8. Mostly questions 1 through 6 though, or exercises 1 through 6. A little bit of 7 and 8, but not as much. Okay? So we're going to keep going. We're going to exercise 7 and 8 is what you got to get done over the weekend. So maybe write that down somewhere. It's also going to be in Canvas. It'll tell you, hey, exercise 7 and 8 needs to get done. All right, a theorem. A theorem. Page 14, where you guys should be. Who wants to read what a theorem is for us? Who hasn't read today or said anything? Go.
A theorem is a statement of mathematical truth that can be proven.
Okay? This might actually answer our question for part of yours, James. Okay? If P then Q is true, if and only if the disjunction or conjunction, what's this? Only if we have P with Q has the same truth table as Q. Blah. Okay, so they're saying this statement right here. So we got this theorem 1. Highlight this right here, like how I have it highlighted, or circle it, or underline it. This is the theorem. A theorem is a statement that can be proven. Okay? This is the great thing about mathematics, is we don't take things by just saying, well, we think that works every time. We know something works every time when we use it, like the Pythagorean theorem. You guys heard of that?
Yeah.
Does anyone know it?
Plus b squared equals c squared.
Good. So the Pythagorean theorem is a popular theorem that you guys will hear going into 8th grade, right? 8th. Okay. 7th, I don't know if you did it. I know in 8th grade you sure did this. But what this theorem says is if you take a side length of a right triangle, square it, plus the side length of another right triangle, square it, you get its hypotenuse squared. Its longest side squared. Okay? So if I have a right triangle, this theorem says if you take A, and this is B, and this is side length C, if you take these side lengths and square these two and sum them, you get this side length squared. You guys know what a little squared means? You guys know what this means? Yeah. If I have a squared, 2 squared equals 2 times 2, okay? So that's what this is showing, but with letters. A theorem is a fact. It works every time. Huh? This one is just a little more simple for you right now, I'm hoping. It's a little more familiar with what we're going to do. So there's different kinds of theorems. In math, this theorem works every time, this triangle. The theorem you have highlighted on your paper, okay, ignore the triangle one now. The theorem you have on your paper, it's a rule. It's a fact that works every time because it can be proven. This one I just showed you, it can be proven. It can be shown that it's going to work every time no matter what. Like there's no ifs, ands, or buts. It has to work every time. So that's the beauty of a theorem, is it's true no matter what, because it's been proven. There are some things like in science, in like your biology classes and your chemistry classes maybe, other classes or other subjects where you have different ideas that aren't necessarily theorems. They're not facts. They're just inferred to be true, or they haven't proven it yet, but it works quite often. A theorem works every time. It's true no matter what, because it's been proven. So what we're going to look at is a theorem, and we're going to prove it. There's different ways to prove theorems. Okay? One way is just to kind of talk about it, break it down. Another way is to write paragraphs about it. Okay? I read a story about a guy named Andrew Weil. Okay? He tried to make a theorem, or prove a theorem. It was 800 pages long, his proof was. Okay, and it took him like 10 years. We're not doing those kind of theorems. We're not proving those kind. we're going to look at proofs of theorems that have already been proven. This guy, he tried to prove one that had never been proven. But there's other ways to prove theorems. This is going to be one way that we're going to look at. And then we're going to look at 2-column proofs later in the summer. So theorems are going to be a common thing for you guys. So when we see theorem 1, we're going to think about that as fact 1. This is going to be important for you to know. Highlight it. This is what we're trying to prove. The highlighted statement is true, no matter what. It's a true statement, but we're going to try to prove it. So it says proof of theorem 1. Whenever you start a theorem proof, you have to title it. I want you to write off to the side here. We have to title our theorem or start our theorem. Start proof. Start proof. That's going to be that up there, okay? Proof of theorem 1. That's how you title it somewhere. Okay? What we're going to do, this is our goal when we have a proof. In this particular proof, our goal is to show that if P then Q is true, then the disjunction of P and Q have the same truth table. It must also be shown that if P or Q and Q have the same truth table, then if P then Q is true statement. It sounds like a lot of jumbled stuff, right? Okay, questions?
So I was just going to say that you said that if P then Q is true, then P, you said and instead of or.
Whoops. P or Q and Q.
Yeah.
So P or Q. So this statement and Q have the same truth table. Okay? That's what we have to show is that if this is true, then this and Q have the same truth table. And that's what we're going to look at is this truth table right here. Okay? Did you have questions?
Oh, yeah. I was just going to comment, yeah, that theorem is true, that is true.
Say it again.
The only way the theorem is true if everything like it is true.
Yeah. So we're gonna we're gonna make a truth table. So they've already made it for us. Look at the truth table here. Let's make sense of it. Okay, this is the hard part of this class. Is some of you start going off in la la land when we start talking too much. Okay, I'm sorry, but we have to talk about it. So get out of la la land. Make sure you're here. Okay, those of you in la la land. Okay, truth table. We have P and Q, right?
Yes.
The only options for P and Q are to be true, 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 false, false, true, or false, false. These are the different scenarios for P and Q. So we kind of think of this part as separate than this part. So now we're going to look at P or Q. Well, remember on a disjunction, the only way a disjunction is false is when? They're both false. Okay, so everything else is true. If we have one true somewhere in this disjunction, true, true, true. Good? Our goal is to have P or Q and Q have the same truth table. So now if we look at this, if P then Q, we have true, false, true, true. Because on our conditional statement, the only way the conditional statement is false is if we have a true then a false. Yes? So we've got our statement here and our statement here. We're going to make sure we remember these two statements. Questions so far? Okay? Now let's look at part 2. Yes?
Does it not prove that this theorem is not right?
This is the first part of the proof. We're going to keep going.
No, but
Just at the end. Let's get to the end first. Then ask again. But yes, you're saying that those truth tables aren't the same, right? Okay. So if P then Q is true, okay, if we look at this, if P then Q is true, then P or Q and Q have the same truth table. So the second part of the proof, we look at this truth table. Same truth table, all right? Okay, so we look at our statement here. Likewise, this is the key. In cases where P or Q and Q have the same truth table, if P then Q is true statement. Therefore, the theorem is proven. So, let me get where I want. see on your paper, these are, so look at rows, I should roll this down. If you look at rows 1, look at row 1, row 3, and row 4. What's our goal? If we look at if P then Q, okay, P and Q is true here, here, and here, yes? In this case, whenever these guys are true, it's only true if Q and P or Q are the same. P or Q and Q. True and true, right? P or Q and Q, those are the same. So this is true. False and false, so this has to be true too.
Okay.
We good there?
Yep.
So look at the rows. Okay? Questions? Yeah.
I'm just kind of befuddled that they're saying that false true and that P Q as false true is true on the if P then Q, because that's basically saying that if this is false, if this false thing.
Right. And that's something I told you I can't give you a better answer till Monday, right? Right? You're going to stick with it for now and just assume it's true. And I'm going to try to find a better explanation for you, okay? But the rule is, if it's true then false, then this is false.
Okay.
Okay, so that's the only way that if P then Q is false. I see you're confusing. I don't know how to explain it any better yet. Does that make sense? Yes.
I just think of as logic as a fun but weird subject, like confusing.
Right.
Because like at first it doesn't make sense, but once we get to the conditional statement, it really doesn't make sense until there's like a false, 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 and then it's true, and then you're like, oh, that's really logic. But the rest of it's like, what are you talking about?
Well, true and true is true, right?
Well, yeah.
True. Okay, James is saying he's having a hard time understanding the false true is false, right?
No,
Or no?
number 3.
I'm looking wrong. Oh, 3. Yeah, sorry.
A true false.
False true is true. Sorry. But yeah, I'll get more on that on Monday, okay, bud? I gotta come up with a better way to explain it for you, and I don't know yet.
I think I might have kind of like a so how I think of it is if the second, whatever the second one is, so like if say if it was if P then Q then this or something, then I always think of like the second one, whatever that one is has to make it that one, unless it's two of the same things. So, like, if it was false true, that would make it true, or true false, that would make it false, because the second one is true or false.
Well, I'd say that's a nice way to explain how
Here's how I say it. That's a nice way to explain how, but it's not a good way to explain why.
I agree. I think that's a good way to like remember it, but maybe not.
Yeah, it's a way to remember it, good
Yeah.
way to explain how, but why?
I just learned to know the question.
You guys are asking some good questions, and you're getting some good explanations, so I appreciate it. So, like I said, on Monday I'll try to get you more on that, a better explanation. But right now the rule is, if you have a conditional statement and it's false and then true, it's going to be true. The only way the conditional statement's false is if you have a true false. Our proof we're looking at, we're saying that this statement's always true if we have P or Q and Q. So if we have P or Q, and the Q is always going to be the same as our statements P or Q in these 3 cases, okay, in these 3 rows, then our conditional statement will follow as true. Okay? And it has, the reason this works, this little statement works, is because of the idea of this, of the true false being false. Okay? So you guys don't have to prove this. You just have to try to understand bits and pieces of it right now, okay? We need to know bits and pieces of the proof. In a proof, you need to show why you think something's true, and then give a reason. Well, likewise, in cases where P or Q and Q have the same truth table, which is what we saw here, P, if P, then Q is a true statement. So we showed it here, and then we restate it here and say, well, look, that's what happened. Our statement works. Okay? It's like showing work when you can clearly see, oh yeah, it does work, but you have to explain it. So when you're looking at a proof, it's like putting some English concepts into mathematics. We have to be able to write it in a way that people, when they go read it, they can understand it mathematically. Yes?
Why did you use the second row?
Because the second row is where if P then Q is false. We're only looking at cases where if P then Q is true, true, and true. Make sense? Because our statement says if P then Q is true, right here where I've got it highlighted, see that? Then P or Q and Q have the same truth table. So, well, P or Q and Q are true here, right? And then P or Q and Q are true here. And P or Q and true and Q are false here. They're the same in those three rows. So like, they're both false here, both true here, but here, since the conditional's false, they're not the same. The only time that the conditional's true, if the conditional's true, then these guys are going to be the same. Not necessarily true, but they'll be the same. Okay? Okay, stand up.
Heads up,
Wait, you have to say something.
Just giving you guys a break for a second.
Okay, that's part of my water bottle. Won't go back on.
Oh, don't do it, don't do it. Go back on.
This, it won't work.
All right, Casey.
It doesn't work.
Okay, variations of a conditional statement. So we're still working with conditional statements. Okay, we looked at a theorem. We looked at a proof for that theorem. Now we're going to go back to some definitions. The converse of if P then Q is if Q then P. So the converse, know what the converse is. So if I tell you to write the converse of if P then Q, you're going to write if Q then P. So you're going to switch. If you know the statements of P and Q, so like Santa is jolly and Christmas is on July 4th, you'd say if Santa is jolly, then Christmas is on July 4th. The converse of that would be if Christmas is on July 4th, then Santa is jolly. Right? So you just switch them. So we're not looking at switching. We don't care about the truth value right now. We're worried about switching the order and what converse means. Okay? Yes?
That's the perfect example of that either would be false, because you're saying that if you say, well, Christmas is on July 4th and Santa is not. Well, someone who doesn't know either knows the book, yes, Christmas is on July 4th. It's not, so therefore the logical conclusion, or logical conclusion in my head, apparently this one is not making sense, would be that Santa is not jolly.
Okay. Question?
So, just wondering, if we started with if Q then P, would the Q then P, be the regular conditional statement, or what, or if we like did converse of it,
If this is
it
what
would be the converse? or
if this is what you start with, then this is the converse. If you start with Q then P, then that's the converse. Yes. So the antecedent and the consequent just change. So it depends, whatever, because it doesn't have to be P and Q, remember? It could be A and B, it could be B and A. It is whatever what you start with. To answer your question, yes. Okay. Definition 7, yes.
Why do they call contrapositive positive?
Okay, so on definition 8, contrapositive of if P then Q is if not Q, then not P. It's a conditional statement. Okay? The antecedent and the consequent are both exchanged, so you're going to take the converse of it. Okay? And then you got to take the negation of each statement. So you take the converse and the negation. Why it's named what it is, I don't know for sure. The inverse of your conditional statement is just taking the negation of each of the antecedent and negation of the consequent. Okay? Yes?
So is the only purpose of saying inverse instead of
Hey,
negation?
you three, I need you to pay attention because this is where you're going to get lost. Okay? You've been talking the whole time. Please stop. If you got a question, let us know. Yes?
So is the only for doing saying inverse instead of negation is because like inverse refers to both of their negations instead of just one. Like inverse refers to P and Q's negation instead of like when you say negation is Q's negation.
I guess I misunderstand your question.
I'm just wondering why they bother saying inverse instead of negation, because that just makes it would make it a lot simpler if they just use one.
Because if we're using the negation of a statement, we're talking about just the one statement. So negation is specific to one statement. Does that make sense?
Yeah.
So when you're taking the negation of both statements in a conditional statement, then they call it inverse. So you know that you're referring to a conditional statement. Does that answer your question?
Yeah.
Okay, the three definitions. You need to know how to apply these. So if I give you guys a conditional statement, you need to be able to write the converse. You need to be able to write the inverse. You need to be able to write the contrapositive. Okay? Questions?
Contrapositive is, so contrapositive is going to be the complete opposite of the statement, right?
The antecedent and the consequent are exchanged, and they're negations. Break it down just right there for now. Don't look too much further into it yet. Just know how to say, okay, I got to switch them, and I got to take the negations to write it. So I need you guys to be able to write the foundational part of it and understand how to write it first. Does that work? Okay. So if we look at our little table here, this might help some of you remember what each of them do. Okay? If you're going to have a conditional statement, okay, you switch them on a converse and a contrapositive. You negate them if it's inverse and contrapositive. So contrapositive, you switch and negate. Okay? On inverse, you only negate. On a converse, you only switch. So a little table will kind of help you. Okay, example. If Santa's jolly, then Christmas on the 4th of July. So if we take this, we take the converse, if Christmas is on the 4th of July, then Santa's jolly. We switch them, right? You see that? Converse. Inverse, we're going to just negate them. If Santa's not jolly, then Christmas is not on the 4th of July. Okay? Contrapositive of our conditional statement. If Christmas is not on the 4th of July, so we've exchanged, and we're negating, then Santa's not jolly. So you have to be able to write each statement. What I'll do on the quiz, you guys will get a statement, conditional statement. You'll have to write 1, 2, 3. Converse, inverse, and contrapositive. Okay? Okay, this is the truth table for conditional statements. This is like a fact. Okay, this truth table, when you guys are doing like larger problems, you're going to want to star this page because you're going to want to come back to this truth table. This truth table is like a gold mine. Yes? Yes. I believe so, yes. Okay. So the truth table this works. You want to like keep, because you don't want to have to make a truth table each time, so you can refer back to this. You want to be able to refer to this truth table. If P and Q are true, true and true, your conditional is true, your converse is true, your inverse is true, your positive is true. If we look at row 3, if our conditional's false, or sorry, if our P is false, Q is true, not Q to be true, and then Q, not Q to be false, then our conditional is true, converse is false, inverse is false, contrapositive is true. Okay, this is a table. You don't have to memorize it. We're just going to have it there for us for right now. Remember, these are all conditional statements still. But they're types of conditional statements. This is our original conditional statement. This is our converse, our inverse. So the rule still applies if this is, what happens on a conditional when we have a true and a false? It's false, right? Okay? On our converse, if we have a true and a false, what's going to happen on our converse? So think about this. Look at the converse here. I'm asking you, if you have a true then a false, this means conditional, yes? So if you have a true then a false, you're supposed to get what?
False.
False. Look at this. Q is true, right, for this row, right? Okay. See where this matches up? Q is true, P is false. So our statement's false. Okay, look at this one. Not P, not Q. Let's assume this one's true and this one's false. So I'm going to look over here. Not P is true right here. Not Q is false right here. True, false. This should be false. Good. You guys see where I'm going with this?
Yeah.
Okay. Not Q, let's assume that's true. Let's assume not P is false. So I'm going to come over here and say, okay, where's not Q? Not Q is true right here. Right? And right here. Yes? Okay. Not P is false only right here and here. They match up here. True then false gives us false.
Alright.
Yes?
So I'm confused on the second row for converse. Second, where P is true, P is false. It's the converse, second row.
So which row?
Second row.
Okay? Where we're at?
Converse.
The converse. Did I highlight that wrong? So we want Q to be true, true, and P to be false, true, false, false. Oh, I looked at the wrong one. Oh, sorry. That's what you're seeing. Okay.
It's on the second row down.
I got too many arrows going on here. So you're looking at the converse. So we're assuming, and we know on a conditional statement, these are all conditionals, these little arrows, right? What I'm trying to point out to you guys is when the first one's true, the second one's false, the whole value is false, right? Okay, converse. Where is Q true? Well, Q is true here and here, right? P is false right here when Q is true. So we want this one. Okay, we have a true then a false, so the converse has to be false. Does that make sense? Is that better? Okay. So you're looking at where you have to look at the row where they both happen. I think I circled the wrong one when I did it the first time. Right, but you're looking here. If I have a false and a true, the conditional's true. Okay? Which, because the conditional, this would be false true is P then Q. Yes. Okay. Questions? Heads down. Okay, Okay, who's totally lost right now? You're out in left field without a glove. Okay, you're kind of lost. Okay, this is making sense to you. Raise your hand. Hands down, heads up. Okay, people are lost. I need questions. Yes? Like I said, I can't answer that till Monday. Can't give you a better explanation until Monday. Assume right now, though. Okay, just assume. If you have true, false, it's false. Everything else is true. Okay? Is that okay? Just accept the fact until Monday, and I'll give you a better example. No, because I'll give you a better example, and it'll still be true. Still going to be true on Monday. Okay, questions other than that one? Okay. Yes.
Well, I was reading through the homework and it said on number 5 express if A then B in two other ways that don't affect each side of the original statement. What does that mean that it doesn't affect the truth value?
You're ahead of me right now?
What?
You mean, like, what number?
On exercise 7 it says on number 5.
Not there yet. When I get there.
I just
I get there, yeah. Okay.
What is this vehicle from? This, what's that from? I don't remember.
Some commercial.
I know, but like.
Okay, alternate ways of expressing a conditional statement. Okay, other ways to express if then. Okay, we have if P then Q. That's what we've been working with. P only if Q. That's another way to say it. P is a sufficient condition for Q. Q if P. Q is a necessary condition for P. So these are just different ways to say if P then Q. Don't worry about it, about writing it. I just do if P then Q when you guys write something. But if you see something written a different way, then you know they're talking about a conditional statement. Okay, consider these statements. A triangle is isosceles. The triangle has at least 2 congruent sides. So, if P then Q is written, if the triangle is isosceles, then the triangle has at least 2 congruent sides. What's an isosceles triangle? Yes.
It is, it's a triangle that has 2 sides that are the same.
Which congruent means, you don't know this, write that there. Congruent means same. So an isosceles triangle has 2 side lengths that are the same. So if we take this statement, if P then Q is written as if a triangle is isosceles, then the triangle has at least 2 congruent sides. Good. We can also rewrite it. I'm not going to read every one of these. These are just examples. And it's saying, hey, look, you can rewrite this conditional statement those ways. Okay? You can rewrite them as a triangle is isosceles only if the triangle has at least 2 congruent sides, and so on. So, this example 10, is an example of these alternate ways of expressing a conditional statement. So, different ways to write the same thing. Okay, the reason we like that is because if we could write it a different way, it might make more sense depending on where you're writing. Okay, mathematicians, when they write these proofs and these ideas, depending on how they're writing, it might make more sense to use one of these other statements. Okay? Questions? That's all this example is showing you, is there's different ways to write the same thing. Questions? Okay, exercise 7. Fill them in, ready to go. You got 4 minutes. You guys about number 5, right?
well, so I think I figured it out. So I think that is just different words. Yeah, I thought
Very good. If you understand how to write a converse inverse. Okay. Come back here. When you write a converse of a statement, you have if, P, then Q. So you start with this. You're going to write the converse to be if, Q, then P. You just switch it. So if Santa is jolly, so it says, if Santa is jolly, and Christmas is on July 4th. The converse of that is just switch it. Yep. Switch the antecedent and consonant. Then the inverse of that would be if Santa's not jolly, and Christmas is not on July 4th. So you just take the negation of the first part of you keep the same order. Negation. That's what's nice about this little table. So the ones where you negate are the inverse and contrapause, so they're negating one here. And the switch row right here is the converse and contrapositive. So the contrapositive is where you switch them, then negate. Yes. Does that help? Sometimes it just helps to talk through it again. So that, you asked a great question. I think that's a question. Now, slide on the floor. Yep. If you are to live. So this one, if we come back here to this idea, this is just showing the truth table for, if you look at this row, okay? If you have a true, then not P, not Q is false. Then it shows you the results of addition. Don't use the whole tree. One act each situation. First situation is row one. Okay? In row one, if you have a true, false, then you can say, well, just be that true. That's true. If true, then true. So it's got true. If true, then you have a true. Then you say, well, if I have a true, false, true. These are all the different combinations. You say here, then these Good. Yes, but I'll answer your question. I'll answer your question. You can try it. But if I answer that question, the reason I answer your question before is if I answer number 5 before we talk about it, the rest of the rules are all aware. Yep. Okay, number 5. All you're doing on number 5 is you're using that little rule we just looked at. The different ways to write the same thing. Number 5 is saying, hey, look, if you have if A, then B, rewrite if A, then B in a different way than saying if A, then B. Use only if, or use just one of the other ideas there. Okay? So you use one of the other ideas that are there. Yes?
So if I put, for that one, the answer to number 1, and then, if I do put if I put, if humans need water to live, then water is a natural resource, and then for the second one, I put, if water is a natural resource, then humans need water to live, would that work?
No, don't use the same thing you use in number 1. So you got 4 guys.
So we could use P or if Q and
Yes.
Q if
Yes, you could say On number 5, you could say humans need water to live only if water is a natural resource. You don't want to use the same example used in number 1 on number 5. Okay, here are the answers for 1, 2, 3, and 4. Actually, does everyone have 1, 2, 3, and 4 done?
I got all of them done.
No? We'll talk about that on, I'll give you the answers on Monday for that. Let's just do that.
Can you teach us 8? We still have to do exercise 8 or just 7.
Okay, we don't have enough time to do the next section. We'll do that on Monday.
So we only have to do,
We don't have to do 8.
7 over the weekend?
Exercise 7 and 8 are due on Monday. So we'll finish it so you can do number 8 by the end of the day Monday.
Oh, okay.
Make sense?
Yeah.
So if you did number 7 just barely, you're where you're supposed to be.
Okay, but if I do number 8, it's fine if I know how to do it.
Yeah. Okay. Here's what you need to do over the weekend. Finish number 7 if you're not done. Next, don't put stuff away. Listen. You need to study everything up to this point. Okay? That's what your quiz is on Monday. You have 5 minutes for the quiz. So just like the exercise there, it's only going to be 1 page, right? Exercise 7 is 1 page, right?
Yeah.
I gave you 5 minutes. So you guys we've only been taking 5-minute increments whenever I give you time to work. So you're used to what 5 minutes is like. Okay, I might give you a little bit more than 5 minutes, but we can't do too much because we have short class periods. Okay? Hey, good job today. Great questions. Great week. You guys enjoying SU prep?
Yeah.
Learning something?
First day was great. That's all we had to do was
Good. You guys have fun on your field trip tomorrow, those of you that are going.